How many numbers would you need to describe the Moon? To begin with, it is pockmarked with a wide variety of craters from different asteroid impacts over billions of years. A similar exomoon orbiting a similar exo-Earth in a different solar system, even if superficially alike, would have a completely different pattern of asteroid impacts. To characterize each precisely, at a minimum, we would need to give two coordinates, longitude and latitude, for every one of the thousands of craters, along with the size of each crater. Very rapidly, we find ourselves needing thousands of numbers to describe a moon, even before we start talking about the chemical composition of the moon's surface and how that varies in different regions. The number of numbers we need quickly expands from thousands to millions and beyond. And that is just a moon, one of the comparatively more simple objects in the cosmos. How many more numbers would it take to describe a planet, a star, a nebula? Or indeed, how many numbers would it take to describe the most massive single object in the entire universe, a black hole? The answer for these monsters may surprise you. Three numbers and no more. 3 numbers and only 3 are sufficient to define them completely. On the one hand, this makes black holes seem like very simple objects. Only 3 parameters are necessary to classify them: their mass, electric charge, and angular momentum. Know these 3 numbers and you have everything. Anything and everything in the universe can go into a black hole. And yet, once it is formed, all of that information is reduced to 3 numbers. How the black hole was made and what went into it becomes almost irrelevant. And so the question is, given this almost uncountably large number of possibilities for making a black hole, how can they then be described by just 3 numbers? Where has all the other information gone? Has the black hole forgotten about its origins, or does this information survive in some hidden form? Many of the atoms that make up who you are can actually be traced back to the very first second of the Big Bang, 13.8 billion years ago. It is fascinating to trace our origins. And that's why MyHeritage is such a fun service to sign up for, our sponsor today. MyHeritage makes it fun and easy to build your family tree and discover your origins, and you might also find new relatives. As well as this, I matched with someone on father's side that opened up whole new branches. Within 5 seconds of logging on my family tree, already had 72 people. In the 1780s, the position of a country priest in the Church of England was not especially demanding. But to those who wanted something more, there was time to think deeply about the world around them. And this is how English parson John Michell spent his time. A century earlier, Isaac Newton's theory of universal gravitation had shocked the scientific world. Newton had also argued that light consists of tiny individual particles, so gravity should be acting on these tiny particles of light. Earlier, the astronomer James Bradley had measured the speed of light, and measured it well. The speed of light was known to be around 180,000 miles per second. Michell also knew that an object thrown upwards would fall back down. But if thrown upwards fast enough, it has enough speed to escape the Earth's gravity and reach space. For the Moon, 2.4 kilometers per s. For the Earth, 11.2 kilometers per s. For Jupiter, just under 60 kilometers per s. And for our own Sun, roughly 617 kilometers per s. But imagine an even denser body. What, thought Michell, about a body which was sufficiently dense that its escape velocity exceeded the speed of light? For such a body, light emitted from the surface would not be able to escape. Michell's work was way ahead of his time, and his results seemed no more than an abstract curiosity. It therefore went into the scientific back drawer and stayed there for 150 years. And the next time this drawer would be opened would be in the miserable trenches of the First World War, where the German astronomer Karl Schwarzschild pondered the equations of Einstein's brand new theory of general relativity. Having developed his special theory of relativity in 1905, 10 years later, Einstein succeeded in extending it to include gravity. Schwarzschild looked for the simplest possible solution he could imagine, a spherically symmetric spacetime around a concentrated point-like mass. As the distance from the mass comes in from infinity, there is a critical distance where something strange happens. This critical radius, known as the Schwarzschild radius, indicated the presence of an event horizon for the black hole solution, a spherical shell at a certain distance. No object can move faster than the speed of light. Outside the horizon, an object moving at the speed of light away from the black hole can escape. But any closer, there could be no escape, not even for light. Any astronaut that crosses the black hole event horizon finds him, or herself, on a one-way passage towards the center of the black hole. Once inside the event horizon, time always points towards the very center of the black hole, until they reach the singularity itself. The Schwarzschild radius for our Sun is about 3 kilometers, and for the Earth it is less than a centimeter. A human's Schwarzschild radius is on the order of 10 to the power of minus 23, smaller than the nucleus of an atom. And were all the stars and gas and dust within the Milky Way somehow condensed into a radius less than 0.2 light-years, a truly mammoth black hole would eventually form. Schwarzschild's solution was found in 1915, but as with Michell's work for half a century seemed merely an intellectual curiosity. The comments of the American physicist Richard Feynman give an idea of what people thought about it. But the state of the field described in Feynman's caustic summary would all change in the late 1960s. There was one source that was especially bright and compact, known as Cygnus X1. There was only one good candidate to explain the data: a compact black hole. In 2015, colliding black holes were first observed as the gravitational waves emitted from their collision was picked up by the LIGO Observatory. Since the first discovery, many more black holes have been discovered. In offices and on blackboards, the theoretical exploration of them become a bizarre new playground for the most extreme questions in the cosmos. This Hawking-Penrose collaboration also changed how relativists thought about space and time through a novel conceptual visualization called Penrose diagrams. Among the human icons of 20th century physics, Stephen Hawking holds a privileged place. At the age of 21, he was diagnosed. He threw himself into his work with a desire to achieve something and leave a legacy. Together, Hawking and Penrose proved a set of key theorems. The inescapable endpoint of that collapse would be a singularity. This result was not about intuition or hope or expectation, it was a proof. Nothing is more familiar to us than the human face. How many numbers and how much information would you need to specify any human face completely? A lot. Something much less familiar and apparently more exotic is a black hole, and yet in a way, they are far simpler. This limited number was not just through a lack of effort. For as physicists studied the equations of general relativity, they proved a result now known as the black hole uniqueness theorem. As the American physicist John Wheeler neatly summarized, black holes have no hair. Behind the mask of the horizon there are an almost infinite number of ways that a black hole could have been formed. And so how do all these starting possibilities end up as just 3 numbers? Let me count the ways. When a physicist hears these words, they immediately feel connected to an apparently totally different part of physics, that of the science of thermodynamics. Gases with their temperature and pressure, black holes with their mass, spin and charge. For both physical systems there are a few numbers. There is a particular quantity which counts the number of such internal states. This quantity is the entropy. The entropy of a system depends on the bulk parameters, and counts the number of internal micro-configurations that can give rise to them. This result dated back to the early 1970s, first suggested by Jakob Bekenstein, and later fully developed by Stephen Hawking. Bekenstein asked, "If you mix hot and cold tea and then throw the cup into a black hole, does the entropy disappear?" This went against the almost sacred second law of thermodynamics. Eddington, could the overall entropy of the universe still increase if things disappear into a black hole? This set Bekenstein thinking. He concluded that black holes should indeed have an entropy, now called the Bekenstein-Hawking entropy. For a black hole, the entropy is actually set by the area of the horizon. Hawking proposed that black holes also have a temperature. The temperature of a black hole changes inversely with the mass energy of the black hole. Big black holes are cold, small black holes are hot. A typical astrophysical black hole with a mass slightly larger than our Sun is around 1/1000th of a degree, but a much smaller hypothetical black hole could have a temperature of hundreds of billions of degrees. Black holes become hotter as they give off heat. As the black hole loses energy, it gets hotter, eventually evaporating in a blaze of radiation. This is opposite to our intuition. A normal fire cools as it loses heat. Where does this heat come from? Hawking showed that quantum effects near the horizon produce radiation. Essentially, the black hole loses mass energy as radiation escapes, so it cools in mass but heats in temperature. The radiation is tiny for astrophysical black holes, virtually impossible to detect directly for large ones. But for hypothetical small black holes, the emission could be dramatic. If a black hole entropy counts internal states, what are these states? Where is the information? This leads to deep questions at the interface of quantum mechanics and gravity. One powerful idea is the holographic principle, that information about a volume can be encoded on its boundary. If true, the horizon area being proportional to entropy makes conceptual sense. But this raises the famous black hole information paradox. Does information get destroyed? For decades, this was one of the hottest debates in theoretical physics. Resolving it likely requires a complete theory of quantum gravity. Many approaches are being explored. Ideas like holography, string theory, and loop quantum gravity all contribute pieces to the answer. Observational advances, from LIGO to the Event Horizon Telescope, have turned black holes from thought experiments into measurable objects. They provide new windows to test these ideas. Recall, to describe a black hole you need only a mass, an electric charge, and an angular momentum. And that was it. That was everything. In 1963, the Kerr solution appeared, an uncharged black hole with angular momentum spinning on its own axis. Think of a supermassive ballerina, rapidly spinning, arms in, collapsing into a rotating singularity. Soon after Schwarzschild, the Reisner-Nordstrom solution described electrically charged black holes. These are the main classical families of black hole solutions. Why did there seem to be so few black hole solutions? The allowed solutions were tightly constrained. This property was formalized as the black hole uniqueness theorem. John Wheeler again, black holes have no hair. All messy details are hidden behind the horizon. Whatever falls in, the external classification reduces to those three numbers. For other objects like quasars and stars, there are trillions of descriptive parameters. Not so for black holes. An enormous variety of formation histories converge on the same external description. So what is inside a black hole? Classical relativity points to a singularity, but quantum gravity may change that. All classical trajectories end at a singularity, but physics there is not settled. Does information survive in a hidden form? Perhaps encoded at the horizon or in subtle correlations in Hawking radiation. Quantum entanglement plays a leading role in modern debates. Recent theoretical developments, firewall debates and AMPS paradoxes, probe whether the horizon is smooth or violent. These are active, unresolved questions. Observations can test space-time close to the horizon. Imaging, timing, and gravitational waves give clues. Gravitational waveforms encode mass and spin precisely. The three numbers in action. If information is encoded in radiation, black holes act as slow information engines returning content to the universe. How can a small surface area store so much information? That's the fundamental puzzle. Practically, astronomers classify black holes by these few numbers, making them surprisingly tractable for observation. Measurements constrain mass and spin tightly. Charge is usually negligible astrophysically. Philosophically, it's striking. Black holes compress infinite histories to three numbers. What does that say about the nature of information in the universe? To answer fully, we must blend general relativity, quantum mechanics, and statistical physics. Next, how temperature, entropy, and radiation all fit together, and what the universe might be telling us. Recap. Black holes are simple externally, complex internally. Continue to the next section for entropy and Hawking radiation in detail. Let us return to the simplest question. Why do black holes have a temperature? Hot objects radiate. Hawking showed black holes radiate due to quantum effects at the horizon. As radiation escapes, the black hole loses mass, which raises its temperature, accelerating the process. For astrophysical black holes, this is enormously slow, but in principle leads to complete evaporation for tiny ones. Bizarrely, the lightest known black holes are far hotter than the distant giants, though still extremely cold by everyday standards. The heaviest known black holes are around 100 billion solar masses. The smallest are a few solar masses. Detecting Hawking radiation from astrophysical black holes is far beyond current sensitivity, but analog systems in labs have reproduced related effects, giving confidence to the theory. If Hawking radiation carries subtle correlations, information could slowly leak back out. Modern proposals suggest early radiation is entangled with later emissions in complex ways. Alternatives like firewalls propose dramatic changes at the horizon. Others preserve smoothness via subtle unitary evolution. The debate continues. Experiments may one day tip the balance. Black hole thermodynamics connects to deep cosmological questions. Entropy of the universe, arrow of time, and information bookkeeping. Black holes store enormous amounts of entropy compared to ordinary matter. Imagine every encyclopedia, every databank poured into a black hole. Somehow the horizon accounts for it. This is why entropy proportional to area is so surprising and suggestive. Takeaways. Black holes are simple externally, thermodynamic with entropy proportional to area, and radiate quantum mechanically. Observations and theory together push our understanding forward. Where has all the information gone? The answer remains one of the deepest puzzles in physics. It asks us not just about black holes but about what information and reality truly mean. If you enjoyed this dive, subscribe for more explorations of the cosmos. So, sign up for a 14-day free trial and enjoy all the amazing features MyHeritage has to offer. Thanks to MyHeritage for supporting educational content on YouTube. Sources and suggested reading appear in the description below. Watch next, Black Holes, Entropy and Information, recommended. 3 numbers, infinite histories. The universe keeps its secrets and invites us to ask. Thanks for watching.